All right, so today's lesson is going to be on polarity, and we're going to talk about the polarity of bonds and the polarity of a molecule itself. We have two types of polarity. We have nonpolar and we have polar. Nonpolar is when electrons are shared equally, and polar is when electrons are shared unequally. All right, and we're going to start with looking at number 4, water, from our homework sheet. All right, and what we notice here, water has the oxygen and 2 hydrogens. Now, this is based on electronegativity. All right, and if you'll remember, electronegativity is how likely is an element to share. How well does it share electrons? And we know that electronegativity is going to decrease as we move down the periodic table and increase as we move across the periodic table, with fluorine being the most electronegative element. Now, when we talk about what is more electronegative, we are going to be making some assumptions here. These assumptions may or may not be correct, but we're going to just make those basic assumptions in terms of electronegativity for the purposes of this class. All right, so oxygen is directly beside fluorine. So there's a high probability that oxygen is more electronegative than hydrogen, which is way over here on the periodic table. So oxygen is more electronegative. That means oxygen is hogging those electrons. All right, so oxygen does not like to share those electrons. And when we gain electrons, we become negative. Now, the reality is oxygen will occasionally share an electron with the hydrogen. So it does not have the electrons all the time, giving it a partial negative. And there's our symbol for partial, all right, our Greek symbol. When an element loses electrons, it becomes positive. Hydrogen does not have those electrons very often, but it does occasionally get them, so it's not a total positive, it's not a complete transfer, it's just an unequal sharing. So hydrogen is a partial positive. We call this a dipole, meaning the electrons are being shared unequally between the oxygen and the hydrogen. So when we draw our dipole, we are going to draw it towards the more electronegative element. And check this out. When I cover this up, I get a positive, and hydrogen is a partial positive. When I look at the rest of the dipole, I get a negative. Oxygen is a partial negative. So when I compare my bond between oxygen and hydrogen here, again, oxygen is more electronegative than hydrogen, so the dipole is going to go towards the oxygen. Now, the molecule itself, when you think about this, this structure is bent. So our hydrogens are, in fact, in a 3D structure. They are being pushed down. Because of the way they are being pushed down, the hydrogen, the pool of the hydrogen and oxygen, and the pool of the hydrogen and this oxygen, there's not an equality here. All right, these lone pairs of electrons are very negative. There's no pool at the top. The pool is all down here between the oxygen and the hydrogens. So overall, water would be considered a polar molecule. It has polar bonds, polar molecule. When we look at oxygen, for example, these two elements are exactly the same. So there is no dipole. The electronegativity of this oxygen is the same as the electronegativity of that oxygen. So overall, this would be a non-polar molecule. When I look at carbon dioxide, All right, so oxygen is directly beside fluorine. So oxygen is more electronegative than carbon. So my dipole is going to go toward the oxygen and toward the oxygen on this side as well. However, this structure is linear. All right, so these oxygens are in direct line with the carbon. So the pull to the left is equal to the pull to the right because oxygen is the same on both sides. So it's the same pull left as it is right. So overall, carbon dioxide would be nonpolar. When we look at our structure for number 7, nitrogen is closer to fluorine than hydrogen, so nitrogen is probably more electronegative, so my dipole is going to go toward the nitrogen. Chlorine is directly below fluorine. Chlorine is touching fluorine on the periodic table. Nitrogen is not. So chlorine is probably more electronegative than nitrogen. And now we're making assumptions here based upon locations within the periodic table. So chlorine is more electronegative, so my dipole is going to go toward the chlorine. So what do I have? Nitrogen is pulling hydrogen from the top and the bottom, but chlorine is pulling toward the right. So I got this molecule which is being pulled in all kinds of directions, from top to bottom and to the right. So because we've got this pull in all bunches of directions, this is a polar molecule. Fluorine is the most electronegative element. So my dipole is going to go towards fluorine. Fluorine is doing all the pulling. So this overall molecule is polar because the pull is all to the right. So when we do these concepts here, it's really based upon what is happening. And the drawing of the dipoles is very helpful to do this. Now, some textbooks will give you arbitrary values as to what electronegativity values are for the elements, but the reality is there's a lot of discussion, all right, and disagreement between. And then when we do the math to figure it out, some textbooks will tell you this and other textbooks will tell you that. So really, if we can just kind of understand the concept of polarity in terms of bonds and in terms of the molecule itself, that's what we're trying to get at. We're not trying to get into the weeds of the different opinions of textbooks. Carbon is in the center. Fluorine is the most electronegative. And again, I'm just kind of jumping around here for us to get our concepts. All right, so my dipole is going towards the fluorine. Now, chlorine, again, directly below fluorine. So chlorine is probably more electronegative than the carbon. So my dipole goes towards the chlorine. Now, fluorine is pulling equally top and bottom. Chlorine is pulling equally left to right. However, fluorine and chlorine have different electronegative values. Fluorine is pulling more up and down than chlorine is pulling left to right. Because there's a difference between the up and down and the left to right, overall, this molecule is polar. If I had carbon with fluorine around it on all of them, now in this case, fluorine is pulling equally up and down in the same. Fluorine is pulling left to right the same. In this case, because the up and down pull is identical to the left and right pull, it would have been a non-polar substance. So you really have to look at what you are given. It is based upon what you are given. Be careful. Do not make rules. All right, let's flip down to our carbonate. And you'll notice in carbonate, I've drawn it all three ways because I do not care where you put the double bond. You had the option to put the double bond on the left, on the right, or at the bottom. We call this resonance. Resonance is when you have the option to place a double bond. Now, what does that mean? What's happening here is this double bond is constantly switching. It's on the left, it's on the bottom, it's on the right, back to the left, bottom, right. It is constantly switching. It never stays in the same spot. It's not really happy anywhere. It wants to be in all three places, so it just keeps switching around. And what that does is that creates an intermediate link where I have a bond that is shorter than a single bond, but longer than a double. Remember, single bonds are the longest bonds, triple bonds are the shortest. So by switching this double bond and going all around here, what I end up with is an intermediate structure where bonds are shorter than the single. But they are longer than the double. So this lesson has kind of a lot of information. All right, we talked about resonance and got that in there. All right, we talked about polarity. Be careful. We have two types of polarity. We have bond polarity. Let's look at number 17. Nitrogen is closer to fluorine than hydrogen. So nitrogen is going to be more electronegative. So my dipole goes towards the nitrogen. So bond polarity. But then we have the polarity of the entire molecule. Hydrogen is pulling up and down at the same as hydrogen is pulling left to right, because nitrogen has hydrogen all around it, and the pull up and down is the same as the pull left and right. It is a non-polar molecule. So be careful here, guys, because we want to make sure we're not talking about two different things. Is it the polarity of the bond that we're being asked about in the problem, or am I asking you about the overall molecule? It is possible to have a polar bond and a non-polar molecule. Be careful.